Welcome, everyone, to an insightful session exploring the fascinating, yet sometimes dangerous world of shared library interposition, specifically focusing on the LD_preload mechanism. As senior software engineers, system architects, and DevOps professionals, you're constantly seeking ways to build robust, fault-tolerant, and performant distributed systems. Understanding the underlying mechanisms of how applications interact with their environment, particularly how they load and utilize code, is paramount. Shared libraries are fundamental components in modern operating systems, allowing for code reuse and efficient resource management. However, this flexibility introduces powerful tools like LD_preload, which, while incredibly useful for debugging, profiling, and runtime patching, also harbor significant security risks. Today, we'll peel back the layers to understand exactly how LD_preload functions and, crucially, delve into its profound security implications, equipping you with the knowledge to both leverage its power responsibly and defend against its potential misuse. Before we dive deep into LD_preload, it's essential to solidify our understanding of dynamic linking. In the world of large-scale distributed systems, efficiency is key. Dynamic linking, primarily through shared libraries, or dynamic shared objects, DSOs, on Linux, offers significant advantages over static linking. Instead of bundling every single function an executable might need directly into its binary, dynamic linking allows multiple programs to share a single copy of a library's code in memory. This not only dramatically reduces the size of executables on disk, but also conserves precious RAM, as the operating system maps a single instance of the library into the address space of all processes using it. When an application starts, the dynamic linker, often ld.so on Linux, resolves all external symbols and links the necessary shared libraries at runtime, making the application launch faster and easier to update by simply replacing a library, rather than recompiling every application. Shared library interposition is a powerful technique that allows us to intercept and modify the behavior of functions provided by existing shared libraries without altering the original application's source code or recompiling it. Imagine you have a black box application and you need to understand exactly what files it's opening, or perhaps you want to restrict its network access. Interposition allows you to step in before the original function is called. This can involve completely replacing a function with your own custom implementation, or merely wrapping it, executing your code first, then optionally calling the original function to complete the task. This capability is incredibly useful for a myriad of purposes, from debugging complex issues by logging function calls, to profiling performance bottlenecks, to testing scenarios where you need to mock external dependencies, or even patching security vulnerabilities at runtime without downtime for critical services. It's about gaining control over an application's interactions with its environment. Now we arrive at the star of our discussion. This isn't some obscure kernel setting. It's an environment variable that plays a critical role in the dynamic linking process on Unix-like operating systems. When you set the LD preload environment variable to point to one or more shared libraries, you are explicitly instructing the dynamic linker, ld.so, to load these specified libraries before any other shared libraries the program might normally use, including even the standard C library. The magic here lies in the loading order. By loading your custom library first, its symbols, that is, its functions and variables, become available for resolution ahead of identically named symbols in other later loaded libraries. This first dibs approach is precisely what enables LD preload to achieve shared library interposition, effectively allowing your preloaded library to override or intercept functions that would otherwise be provided by the system or other application-specific libraries. It's a powerful override mechanism at the very core of application startup. Let's delve deeper into the mechanics of how LD preload achieves its magic. When an executable starts, the dynamic linker's primary job is to resolve all undefined symbols, essentially figuring out where each function and variable an application uses is located in memory. The process is deterministic. The linker first searches for symbols within the executable itself. Next, and this is where LD preload exerts its influence, it searches through any libraries specified by the LD preload environment variable, in the order they were listed. Only after these preloaded libraries are searched does the linker proceed to look for symbols in the standard library search paths, such as those specified in /etc ld.so.conf or ld library path. If your preloaded library contains a function with the same name as a function in, say, lib.so, the linker will find and bind to your function first. Your custom function can then optionally call the original library function using dlsim rtldnext function name, allowing you to wrap or augment its behavior rather than completely replace it. This granular control over symbol resolution is the core power of LD preload. LD preload is not just a theoretical concept, it's a practical tool with a wide array of legitimate and powerful applications for system architects and developers. For instance, in debugging complex multi-threaded applications, you might want to intercept malloc and free calls to detect memory leaks or corruption, logging every allocation and deallocation without recompiling the entire application. Performance profiling can similarly benefit, allowing you to wrap critical functions and measure their execution time precisely. Imagine a scenario where you need to sandbox an old, unpatched application. You could use LD preload to intercept file I/O calls like open or unlink and restrict them to specific directories, effectively creating a lightweight chroot environment without requiring elevated privileges for the sandbox itself. Mocking network or file system operations during integration testing, or even injecting runtime patches into legacy applications to fix critical bugs without downtime are all real-world scenarios where LD preload provides an elegant and efficient solution. It provides surgical precision over application behavior. While LD preload offers immense power for legitimate uses, this power comes with significant security risks that demand our attention as system architects. Because it allows an attacker to inject arbitrary code into almost any program that dynamically links to libraries, LD preload becomes a potent vector for exploitation. Imagine a scenario where an attacker manages to set the LD preload environment variable for a privileged process, such as a SUID binary. They could inject a malicious shared library that overrides critical system calls like execve to elevate privileges, or open and read to exfiltrate sensitive data. This technique is a favorite among malware authors and rootkit developers, as it provides a stealthy way to hook into system functions, hide processes, or even intercept user credentials. The ability to subvert the standard library's functions at runtime can bypass numerous security controls, making LD preload a serious vulnerability if not properly managed and understood. It represents a fundamental breach of trust in the system's execution environment. Given the potent security risks, it's imperative to implement robust mitigation strategies. The most critical defense is that the dynamic linker automatically ignores LD_preload for SUID and SGID binaries. This prevents unprivileged users from injecting code into programs running with elevated privileges. However, this only applies to SUID/SGID binaries, not regular applications. For critical services, consider static linking where feasible, though this comes with larger binaries and more complex updates. System administrators can also enforce stricter environment controls, such as using execve with a cleared environment to launch sensitive applications, ensuring LD_preload is not carried over. Linux security modules like SELinux and AppArmor can enforce mandatory access control (MAC) policies that restrict which libraries a process can load or which functions it can call. Finally, adopting the principle of least privilege for all applications significantly reduces the impact even if LD_preload is successfully exploited, as the compromised process would have minimal permissions to cause widespread damage. Understanding the theoretical aspects is crucial, but real-world examples truly highlight the impact of LD preload both for good and for ill. Historically, LD preload has been abused in numerous ways. Early Linux rootkits frequently leveraged this mechanism to hide processes, files, and network connections by interposing functions like readr, open, and connect. By providing their own versions that filtered out the malicious activity, they could effectively become invisible to standard system utilities. On the defensive side, developers have used it to create powerful debugging tools like Electric Fence for memory debugging, which wraps malloc to detect heap overflows and underflows. Modern operating systems and security frameworks have evolved, recognizing the dual nature of LD preload. While the SUID/SGID protection remains fundamental, the rise of containerization technologies like Docker and Kubernetes also impacts its reach. Within a well-configured container, LD preload attacks are often contained within the container's isolation boundaries, reducing the host system's exposure, though it remains a concern within the containerized environment itself. The battle between exploitation and defense continues to evolve. In conclusion, LD_preload is an incredibly powerful feature of dynamic linking on Unix-like systems. It grants system architects and developers an unparalleled ability to intercept, modify, and extend the behavior of applications at runtime without touching their source code or binaries. This capability, while a godsend for debugging, profiling, sandboxing, and runtime patching, simultaneously opens a significant attack vector if mishandled. The key takeaway is duality. Immense power carries commensurate risk. As professionals responsible for building secure and resilient distributed systems, it is crucial to understand both the legitimate applications and the severe security implications. Always remember to apply the principle of least privilege, be vigilant about environment variable hygiene, and leverage platform-level security features. By mastering how LD preload works, you empower yourselves to not only utilize its benefits, but also to construct more robust defenses against potential exploits, ensuring the integrity and security of the systems under your care. The future may bring more statically linked binaries or WebAssembly, but dynamic linking and its intricacies will remain a cornerstone of system understanding for the foreseeable future.